Alright, we're going to make a dirt hit kind of explosion. So we're in a brand new Houdini file. And let's just put down a sphere. 1 meter sphere is fine. I'm going to change this into a polygon and frequency to 10. And we will clip the bottom half out of that. And we're going to use this as kind of an animation proxy here. So let's put down a transform. I'm going to change our timeline here to 24 frames. Let's start off by animating the scale. So we'll start off with our scale at 0.1, 1.11. Frame 2, we'll go up to about here, keyframe everything else, and let's also keyframe the translate here. So maybe we'll translate those points up a little bit as well. Frame 3, let's go a little bit more oblong. And let's expand outward just a touch, maybe just a little bit higher. Frame 4, up to about there. And we'll go up just a little bit more. Maybe we'll go back down here to 1.2. Okay, so what we're mimicking here is an explosion that's hit the ground, and then we have this initial burst of energy, and we'll make this a bit irregular by putting a mountain sop on here. Let's try alligator noise with not a lot of roughness. A lot of values up here. Wow. Okay, so bring the height down a bit. Okay, somewhere around here, I think. And we're just going to keyframe all this stuff here. So that first frame here, we'll need to bring the height down quite a bit. And maybe frequency dial that up. Okay, so it's a bit random, but that's all right. We'll see how it looks when we start throwing it into simulation. So I want to put down a trail sop, and I want to compute the velocity. We can try a forward difference. Alright, I'm going to scatter a lot of points on here now. No relax iterations. We'll force a total count of 10,000. That seems totally fine. Maybe we'll go to 20,000. It's not really necessary to have a high count here. And then what we're going to do is put a procedural noise on the points and start filtering stuff out so that we can get a nice uneven distribution of particles to be emitted. So I'll put down an attribute VOP. And we'll put down a turbulent noise. Connect position directly into here and connect our output into CD. All right, we'll promote our parameters. I'm going to change this to sparse. Let's dial up the amplitude. And play around with just a few different kinds of noises, see if I like anything here. Kind of liking alligator here, maybe. See what the negative value of that looks like. It's not that bad. Okay, so let's start filtering points out here. We'll put down a delete and make sure we're at points. Change that to expression and $CR less than 0.5. And let's be even more particular. Let's go to 6 and maybe we can take the amplitude down to 2. Let's go to 3 here. Okay, so what I'm trying to do is basically make sure that when we start emitting particles that we get kind of patchy areas and we don't get this kind of uniformity as the particles are emitted from the surface here. So that seems to be okay, and of course we can continue to play with that. And we'll put down an attribute. Actually, let's see. I'm going to keep the color on here for now. We won't want that for visualization, but I might use that for something else later. So we'll put down a pop network and we'll dive inside. I'm going to turn off the guide and I'm going to scatter onto points, and our birth is going to be $F less than 5. Turn off, well, keep on the grid for a second. I might need to change to a darker background because it's a bit tough to see our particles right now. So let's change to a dark background. So jitter, let's try negative jitter. And now our particles are stopped because we don't have velocity up there, so let's see. We might need that to be a central difference. And let's try the other kind. Let's try backwards. Yeah, then we're stuck at that first frame. So what we should do is grab both of these and let's just offset that by a frame. And then here we'll say that has to be less than 6 or $F is greater than 1. or actually, you know what? We don't even need that. We can just say less than 6, and we can start frame on frame 2. We could also just animate one more frame. So let's just do that. All right, to make it easy, let's just take these keyframes, move it back here, and we'll set our simulation to start at 1, and we'll go back in and we'll just quickly change that back to 5. Okay, so we've got particles moving up. And let's make sure we're playing real time. And now let's put in some gravity. So I'm going to put down a pop force. And force, we're going to put in negative 9.8. And then we'll need a ground plane. Or we can just simply delete everything that's below 0. We should also give these particles a lifespan as well. So let's give them a lifespan that's going to have them die maybe around 10 or 11 frames. We'll see if we need a ground plane once we do that. So life expectancy, let's say 0.4 with a variance of 0.3. Let's see what that gets us. Okay, not too bad. I do think we need a ground plane here, so let's put in a ground plane. And that is going to need a static solver. Then we merge these together, static solver in first, pop solver in second, wire that into our output. And we can just turn the visibility of this off here. Okay, so what this is meant to simulate, or to kind of give the impression of, is this kind of dirt hit here. And what we're going to want to do is convert each of these into a particle, or I mean into a smoke emitter. And what we'll want to do as well, let's kind of help ourselves out a little bit here. By creating some of the intermediate points for us. Otherwise, we're going to have to subset the simulation quite a bit in order to get a decent result. So what I'm going to do is we're going to put down a pop wrangle. And I just want to track the leader number here. So we will create an integer attribute called leader ID equals attribute ID. Okay, now we're going to do a pop. What am I looking for here? Replicate. we're going to go, I believe, into the first input here. For attributes, I'm only going to inherit leader ID. And maybe just a very, very teeny amount of the velocity here. Constant activation I'm going to turn off. Impulse count will say 3. And then for our life expectancy, we'll put this at about 0.5. Merge these in here. And we also want to start off with just a point. So for our attributes, we will add to the inherited velocity, and we'll need a little bit of variance in here. We can try some of these jitters. I don't think they're going to close those gaps very well. So we're just going to have to resort to sub-stepping. And let's make sure as well that this stream has a name, so we will call this trails. Do an impulse count of 4, actually. We'll add a very small amount of life variance in here. Okay, so let's fill in some of these gaps. We'll change substeps to 3. Okay, and then from here, we could start to tweak our emitter shapes here. So maybe we'll play with this mountain shape a bit. Give us kind of a weird thing here. Let's see what that looks like as we simulate it. Kind of a different looking shape. It's not that bad. But we're going to need more substeps. So let's try 6 substeps here. And we'll just keep this as it is. And make sure as well that we only are getting back our pop object from here. So in our object merge, we just want pop object, and that will get rid of the ground plane. And now we're going to cache that out. So I'm going to put down a file cache here. I'm going to connect these. Delete that. We'll just go to frame 24. Go into our hip, into geo, and we will call this dirt hit particles. $f.bgeo, and save to disk. We'll load from disk, and now we see our particles here. Okay, let's save our file. We'll move on to the next step. Okay, let's put down an attribute VOP, and we're going to start dialing in our scale parameters for the particles. So let's make sure we can randomize everyone. We will find the ID, use that as a random value, fit that value, and promote these bottom two here. So we'll call that min scale and max scale. Let's make sure we can alter that scale over life. So I'm going to bind the normalized particle age. Let's put that down here. We will ramp that. Let's call that scale ramp. Make sure that is a spline. Multiply these two together. And export that as P scale. We'll also put down another ramp, and we'll call this density ramp. Use the same n age. That needs to be a spline, and we will export as density. So we're going to convert this into a volume. I'm going to do it slightly differently than we've done before. I'm going to start by putting down a VDB. We'll leave the voxel size here. And then we'll put down a volume rasterized points SOP. So what we want to do is change our scalar attribute from temperature to density. Vector we can leave like that for now. Okay, and we'll change our scale values here. Let's go to maximum scale at, say, 0.15. Here we'll do 0.18, scale ramp. Go full value at the end, and we'll go to, say, 0.3 at the beginning. Density, we want to start with 1, and we'll end with 0. And let's do this on a curve. Be monotone cubic. Okay, I'm going to put down a light just to help with the visualization here. And let's dive back inside. So we'll start playing a bit more with our scale parameters. Okay. So here we could add a little bit of padding. Probably too much. Just a touch. And we can try pumping a little noise in here. Trying to be subtle with it. Let's turn that off for a second. See what maybe displacement's a little better for us. Teeny bit. I'm just trying to break up some of the regularity here. Let's take a look at our voxel size as well for our VDB. Okay, one thing I want to see is what our velocities are doing here. They're kind of all moving forward. Spreading out, moving forward, that might be okay. I'd like to have a little bit more outward velocity, but maybe this will be okay. So I'm just going to bring this down for simulation purposes to 0.1. Or, you know what, 0.7. We'll write this out to disk because this is pretty slow to calculate here. So we will file cache that. And we'll call that dirt hit density start $f.bgeo.sc, and let's save that to disk. Okay, let's load from disk. Great. And now we'll need velocity here as well. So I'm just going to put down a null, and we'll call that density. Move that over. And we will put down a source, fluid source here. And go back into our container settings, and we'll source pump. So we'll just leave this where that is. let's see, where are our particles here? Let's go into our velocity, into our sample distance. Let's just bring this down a bit. And for the sake of simulation speed, I think I'll bring the division size up a little bit here. And we'll cache this guy out here as well. So we'll put down a file cache. And we'll call this dirt hit pump start. $f.bgeo.sc. And we can save that to disk as well. That should take about a minute here. All right, we'll load that guy from disk. Put down a null. And you know what? We forgot one thing here for our pump. So we got to redo that. We need to go back to our scalar volume and build from points instead. There we go. And make sure that we don't have any noise. And that should be fine, I think. So let's just recache that to disk. Okay, great. Okay, let's call this pump. Visualize our density here. Now we'll bring this into a simulation space. So let's build our box to be about this size to start here. Just save the file here, and I'm going to cut the lesson and we'll pick right back up.